so there is this famous 1985 paper by Lyon Robbins, which showed that you cannot do better than logarithmic growth in regret. So the regret will keep growing. If you want to give any guarantees as to optimality, the regret will keep growing as the number of plays increases. As t goes, the regret will grow as log t. Okay, so basically, it will keep growing. So the regret will start growing very fast, but then it will never go to zero. The growth rate of regret will never go to zero. If you want to give any guarantees of optimality, right? So so then there is this paper in '95 from Agarwal and other, which actually gave a policy for learning that achieved this logarithmic curve. Okay, so Lyon Robbins just said that there can be no policy that can do better than this, but they themselves didn't give an algorithm. But so that's an absolute lower bound. We cannot do better than that. And there are many algorithms that achieve that logarithmic regret. Okay? But now people are interested in optimizing constants. People know that big O notation that we have for measuring complexity hides a lot of constants. Right? But it turns out that when you are talking about billions of users coming to your web page and so on and so forth, constants matter. Okay, so now what people are doing is they kind of come up with different algorithms that not just achieve the lower bound. Achieving the lower bound is kind of given, but that optimize these constants in your that's where we are at. And so for the pack analysis, the best known sample complexity comes from this work by Levanta and others. It's called the median elimination algorithm. We'll talk about the median elimination algorithm in a little bit. We still have 15 minutes. So the cool thing about the median elimination algorithm is that it introduced a kind of a round-based approach to solving the Bandit problem, okay, which earlier people had not thought of. Okay. And it turns out that almost all modern Bandit algorithms take inspiration from the median elimination and all round-based algorithms. I'll explain what I mean by that next slide. Let's start off with a very naive algorithm, which we use as a building block for the median elimination algorithm. So I have n arms. Okay. What I do is for each arm, I sample it that many number of times. Okay. I'm interested in providing some epsilon delta pack guarantees. Right? So what I'm saying is, you give me this many samples, okay, I'll guarantee that at probability 1 minus delta, the arm that I give you will be within epsilon of the reward. So within the reward I get will be within epsilon of the reward. So basically the algorithm is very simple. For each arm, I sample it so many times, okay, and then I'm going to output the arm which has the maximum estimated average. Right? The same thing that we did with epsilon greedy. I pull the arms, I find out what is the average of the reward that I'm going to get. At the end of these samples, I'm going to say, okay, the arm that has the highest reward is the one that is the best arm. Okay. So obviously this sample complexity is that into n. Correct? So that's how many samples I draw. And the trick now is to show that this simple algorithm actually satisfies the pack guarantees. Okay. So so this is where it's supposed to get a little tricky. Okay. So how many of you want to actually go through a proof? One. How many of you actually understood the question? Paying attention to the question? Okay, more people. Okay, fine. So meet me offline. Okay. So that's very simple. I mean, I don't know how many of you are familiar with Chernoff-Hofting bonds. It's essentially it's a way of looking at what are called concentration effects here. Okay, so I have n random variables x1 to xn, okay, and so I can form an estimate of the mean, right, of these things by essentially averaging all of these, right. I can take x1 to xn. I'm basically taking the average of the n random variables here. So the probability that this average, okay, is very far from the true mean. Mu is the true mean. Mu is the true mean of the distribution, and a is the distance they are from. So these are basically called large deviation bonds. So the probability that the deviation from the true mean is large, okay, is bounded by this quantity. So that's all this says. Okay. So now what you have to do is basically figure a way of plugging in that that weird expression we had here, right? And then showing that the probability is actually delta by n. Okay. Probability of you making a mistake is delta by n. Making a mistake and choosing some arm x instead of the best arm. Okay, but then you have n minus 1 such mistakes that you can make, because only one arm is the best arm, so n minus 1 arms could be wrong. So delta by n is the probability of making one mistake, but there are n minus 1 such mistakes you could make. So the overall probability of making mistake is delta for large n. That's the idea. We will not walk through that. If you are interested, you can. So the median elimination algorithm basically, so order n, can you do better than order n? Can you do better than order n in trying to find the best arm? Can't. You have to pull each arm at least once. Okay. How can you eliminate an arm without even looking at it? Right? You have to pull each arm at least once, so that gives you the order n there itself. Right? So the problem with the naive algorithm was that we also had an additional n factor, which is the log n. Okay? So we really do not want to have any other factors than n. Whatever additional factors you have, it should be only dependent on epsilon and delta. And otherwise, for very large number of actions, it's very hard to scale. Right? So we wanted to do something that will get rid of the log n factor. Okay? And so the median elimination algorithm used something called action elimination procedure. Right? I'll not go through the whole of it, but I'll just give you the gist of the thing, right? So what you do is you start at round 1, okay? You sample every arm for some magic number of times. Okay? So the magic is, that number is what gives you the guarantees. Okay? You sample every arm some number of times, then you compute the average, just like you did for the other two algorithms. Now what you do is you arrange the arms in order of the average, right? Maybe increasing or decreasing or whatever. Then you eliminate all the arms that are below the median. Okay. So you have all the averages that you estimated from round 1. You eliminate all the arms that are below the median. Now you have exactly half the number of arms that you started off with. Okay. Go back and do round 2. Basically you sample some more times. You sample this, the half the number of arms that are left. Okay. And then again eliminate another half. So like after log n to the base 2 rounds, you'll be left with only one arm, and that's basically your arm. And you can show that this gives you guarantees. It is a little involved analysis, so it goes on for a few more pages. Okay. But what you can show is that the overall sample complexity is n by epsilon squared log 1 by delta. Okay. And then it also achieves your epsilon delta pack guarantees. Okay. So what we have done here is we actually gotten rid of the, it's the same expression that we had earlier for the naive algorithm, except that we have gotten rid of the log n factor. Okay. And people have really not been able to push this further without assuming some other structure for the problem. If you look at it, we didn't make any assumptions about the bandit problem at all. Right? So we assume that we have zero knowledge except the fact that we have n arms. Right? We didn't have any other knowledge about the bandit algorithm itself. Right? So unless you make further assumptions about what you know about the problem itself, you cannot beat the bounds given by these guys so far. Right? Yeah. So this is the thing. But in practice, pack guarantees are very weak. You know? These are like worst case scenarios, right? This will make sure that you never ever go wrong. But in practice, you never face these worst case scenarios. Right? You know, usually in much better behaved settings, and so you can learn usually with far fewer samples than what the pack guarantee tells you. And you can achieve your pack optimality in practice, right, with lot fewer samples. So people are so interested nowadays in transient performance, so we move to the regret analysis setting. So people remember regret, right? I said, how much better could you have done if I had known the right answer from the beginning? If I didn't have to do any learning, if I knew the right answer from the beginning, how much better could I have done? So So that's different, right? From what I am doing now and what I could have done. That is basically the regret. And very simple algorithm that's was proposed by Pete Royer, which in fact is the basis of a lot of regret optimal algorithms nowadays. It's called the UCB algorithm, the upper confidence bound algorithm. Okay. So the UCB algorithm, so essentially what you do is, well, you maintain the average of the rewards that you have seen as you always do, right? So that doesn't change. So you keep pulling arms and then you maintain the average of the rewards you have seen so far for each of the arms. In addition, you also keep track of how many times you have pulled the arm so far. Okay? And that gives you a term that will tell you how bad your estimate could potentially be. So it's in some sense it's like saying that, okay, this is my, and this is just drawing an imaginary line here. Right? Assume that this is my reward. This is the average I've estimated so far. Okay, and the number of times I have pulled it will tell me that the total reward could lie somewhere in that range. Right? Because I need to take a lot of samples before I can be sure of what the actual expectation is. Right? So if my current average is here, I can say that, say my true expectation will be somewhere in that range. Okay? So that range is determined by the number of times I have played it so far and the actual variance of the rewards and a bunch of different things. But this gives us an upper bound on what that range could be. You see that? So usually if you look at confidence bounds, what they say is, okay, you have taken some number of samples, you have made an estimate, the true value will lie somewhere in a range. Okay, that's what the confidence bounds tell you normally. Okay, but those confidence bounds depend on the variance also. But I'm not trying to estimate the variance here. So what we do with the upper confidence bound is, we will assume that the variance can be anything as long as it is bounded variance. Okay, the upper limit I'm giving you is the maximum that thing could be. And now what I'm going to do is, at every point of time, I'm not going to take the arm that has the highest expectation, highest average. Okay, I'm going to take the arm that has the highest upper confidence. So why am I doing that? So that arm has a chance of being the best arm, right? If the upper confidence bound itself is very low, then that I can just eliminate that arm, right? I don't have to take that arm again. So instead of trying to take the arm that has the highest average, I take the arm that has the highest upper bound. And it can be very easily shown that this very simple algorithm, where all I do is I take the average reward and I also keep track of the number of times I have played that arm so far. Okay, just these two quantities, just keeping track of these two quantities, I can achieve that logarithmic regret that Loy and Ravindran talked about. It's a very, very simple algorithm and it actually works well, very well in practice. Okay. So Pete Royer himself has come up with more complex algorithms which push the constants. Okay. We cannot do better than pushing the constants anymore, because this algorithm itself is essentially ln n by 8 by delta j. But delta j essentially is how bad you can be. Okay, so you have the best possible arm, and then you have the next arm, right? So what is the gap? Right? If the gap is very small, right, then your regret, you can think about it. Your regret will also be small, because even though you're taking the second best arm, you're not too far off. Right? But if the gap is very large, your regret could potentially be large, because you're suffering a great loss. Right? And so then yes, that's what I said. He came up with a different algorithm after the event algorithm came. Okay, go ahead. Sorry.
Previous example, the confidence interval, does it depend on the machine, like which machine they use?
Depend on the what?
The XJ, the confidence interval.
XJ is the average that you have. This is, remember the p hat I was using.
The confidence interval is constant for all XJs, right?
No, I mean depending on how many times you have played the arm.
Okay, so if you have played like every machine we have played different number of times, then it might happen that if let's say x2 is greater than x1, but confidence interval of x1 is higher, so
That's the whole idea. Yeah. So if the confidence interval is upper, then there is some chance that that could eventually be, that could actually be the right arm.
Okay, so this means that the confidence interval is a better indicator than mean, than average.
Yes. Yes. So if you look at it, right, the nj is in the denominator. As the nj grows, the confidence interval is going to shrink. At some point, your interval will be very tight around your estimated mean. So at that point, your estimated mean is a good indicator. Right? But at the beginning, when you have very few samples, okay, so the argument here is that the estimated mean could be very bad because the number of samples you have taken is very small, and therefore go with the potential range of the estimated mean.
One more question, slightly unrelated. So we are trying to find the best arm here. Instead of that, is there any approach where they find probability distribution of arms? Like
In the sense?
probability distribution of best arm, like probably there is 60% chance that first could be the optimal, 50% that second could be the optimal.
See, I mean, if your goal is to behave optimally in the long run, right? So you should pick the best arm. But along the way, right? So you could have different estimates as to what is the best arm and so on and so forth. There are algorithms which do maintain probability distribution over the arms when you go along the way. Even in the the simplest UCB case, in the UCB case it never happens, right? But in other problems, yes, yeah. You could maintain a probability distribution along the way. What I'm saying is it's not something which you want to converge to, because that could be one arm that's the best arm. Right? Even if there are two arms which are equally good, it's enough if you find one of them.
So converging means you mean taking any number of trials, taking n to infinity.
No. What I mean by converging is the end of how many ever trials you want to take. Okay. I'm going to return one arm to you. Right? If you look at this previous here, right? So even this, right? So until this becomes 1. So this is obviously going to only take a finite number of steps. Right? At the end of the finite number of steps, I'll give you one arm. Right? So whatever the algorithm ends, I want you to give me only one arm. This should be the best arm. Right? Even if there are multiple arms which are equally good, it's enough if I keep pulling the same arm so that I'll get, in the long run, I'll anyway get the same result. Right? So as a final convergent solution, it's enough to find one arm. But along the way, there are methods that actually maintain distributions over arms which are tied to somehow indirectly related to the probability that the arm is going to be best.
But I was wondering if a solution could be in such a form that there is possible that some probability that first arm is the answer would be we have to choose randomly between first, second, third to get the.
Not in the simple bandit case. I mean, there are cases where you have some kind of state signals and the state signals themselves are not observable. Okay. So there are some instances where you would want to have a probabilistic optimal policy, stochastic optimal policy. But in the regular bandit case, it's always the case that being deterministic one of. And even in the finite MDP case that we talked about in the first part, it's always the case that you can get away with a deterministic policy. There will always be at least one deterministic optimal policy. So only when you have other complicating factors would you need to have an optimal policy that is stochastic. Okay. So I have 5 more minutes, so let me push on. You can catch me here. If you really want to talk after 6. 6 p.m. is gruesome, right? Anyway, so UCB is fine, and I'm not going to go there. I'll skip this. Minus 2 minutes according to my watch. Plus 2 according to yours. Very good. I like your watch. Yeah. So there's another class of algorithms called Thompson sampling. This is basically some kind of a Bayesian approach to learning bandits. Okay. So this will be there in the slides and the references will be there. You can look it up, or if you want. So the next level of bandit, right? So in the bandit case, so far I said you have only actions that you have to pick, right? But then we only want to get rid of the sequential nature of the problem. So you could still have the state signal. It is just that I don't make a sequence of actions. I give you a state, I make one action, I get a reward, and I'm done. Okay? Now the question of generalizing across states comes in. Okay? So I have, say, user 1 comes to my website, I show him a new story, and he clicks on it. User 2 comes to my website, and user 2 is very similar to user 1, right? Then I can use whatever I learned from user 1 for picking stories for user 2. So this possibility of generalization comes in. And why is it important? Because the feedback is so sparse. Right? So if I'm able to generalize from one user to the other, then I can learn better, because the clicks I'm getting are like 1 in 5,000 or something like that. Right? So that's basically, and instead of using one bandit for each user, we want to be able to generalize across users. Okay, so that's the basic idea behind contextual bandits. So we assume that each user is represented by a set of features, and yeah, and then you learn functions instead of learning one mu hat that you had earlier. Now you learn a mu hat. And what was mu hat? Mu hat was the average reward that you will get for taking arm I. So mu hat I will be the average reward you will get for taking arm I. You will learn mu hat I of S, right? Of a state. You will learn a function. So if the state changes, your mu hat estimate will change, but then otherwise you will be doing something like UCB. So that itself will not change. So we first algorithm that explored this was for lin UCB, where you use a linear representation for your mu hat of S. Just use a linear function approximator for mu hat of X, and then you did UCB like action selection. But the trick here was, of course, to show the bounds that regret bounds, log T regret bounds, and so on and so forth. And so basically, they showed that for this add selection problem, okay, which is lin UCB. Okay, so that is lin UCB, and the algorithms that do better than lin UCB, right, are algorithms that actually have more information about the problem domain itself. Right? So they have better description of the problem domain. So things that ran with the same information as lin UCB did not do better than lin UCB. So that's basically the take-home message here. And I have one more thing to show. So that's I'm not discussing that too much. So we also looked at the content recommendation problem earlier. So people set it up very similarly. So the thumbs up and thumbs down that you see there are your rewards. Okay? So if you get a thumbs up, it's a +1. You get a thumbs down, it's a -1. And the rewards are very sparse. Very few people actually rate comments. So again, you generalize. You use features of the text. So people have did. They started off with keywords. Then they looked at lexical features of the comments. I mean, are you using all caps or special characters and so on and so forth. They also use topic models. Okay, they ran LDA on it and then derived the topic distribution, and then they used the topic distribution of the comments and so on and so forth. And then they use logistic regression to model the probability of thumbs up or thumbs down. Okay? And so the algorithm is called log UCB, because once you have this probability, how you select the actions, right, was done in a UCB style action selection. And then what they show here is that in the terms of the thumbs up rate, okay, so how the thumbs up rate grows, the black line is their log UCB. So log UCB does much better than UCB itself and epsilon greedy also. You can see that epsilon greedy does much better than UCB in this problem. I told you that it's hard to beat. And then they tried out different variants of this, where they looked at maintaining some kind of a global model and local model and so many different variants. And then they found out that their one model that combined all the variants into a single model worked best. So I can give you details of that again if you talk to me offline. And I'll skip this. And lots of work, a very active area of research. And so something which I'm kind of getting excited about are this partial extensions of Bandit problems to the MDP case. You know, we talked about the first part of the talk was about a full reinforcement learning problem. Okay, then we just took the explore exploit. Then we added just the state. Okay, then there's small amounts of sequential dependencies you can add, and keep doing that until you go to the full MDP. Right. So can you do analysis with these partial extensions? So that's one simple extension is add a budget. So every time you pull an arm, you lose some money. Right. So now this is going to affect what decisions you can make in the future. So you might want, if some arms are more expensive to pull, you might want to pull them less often than some arms that are less expensive. So you'll have to start planning that so that the future samples also get affected. But this is a very specific form of dependence. So easier to analyze. So there is some work on that also, and that's something which I am interested in pursuing And here's the references I promised. So there's a very good tutorial on bandits. And then John Langford has a fantastic tutorial on learning through exploration. And the recommender system thing, which I told you about. Talks about bandits or recommenders. Any questions? We have time for questions?
If you have any question, please ask.
The basic idea will be all the arms are independent.
Yes and no. And the basic idea, the initial analysis that we talked about and things like that, the arms are assumed to be independent. But in the lim UCB and log UCB cases, as I showed later, they did model dependence between arms. Okay, and that's another thing which I skipped over. I had it on my slides, but I skipped over. There's something called the multi-slot or multi-selection problem. Right? So you don't select a single arm, but you select M arms together.
Yeah, basically, that means the good recommender system should be of that nature.
So
not only one, means several. That's why
exactly. So in that case, yeah, what the set of items you recommend together starts a matrix. Right? So people have, there are formulations that look at that also. You don't have nice theoretical bounds, but practical algorithms that work in that case.
Maybe diversity can be of some use there.
Sure. Yeah. People have, there is some work on modeling that also. Right? So this is specifically these guys in Google and Yahoo have done a significant amount of work in this, and for them diversity is a very important criteria.
Any question more?
So for example, in the case of like Yahoo News, so for example, every hour it has to be updated. So in that case, log UCB would be the only solution, would be the best way to go about, because every hour it has to be updated.
Well, I have another problem. In the lim UCB case, I assume that during the period of prediction, right? During the period of the learning, the arms stayed fixed. So they have some 100,000 arms, but those 100,000 arms stayed fixed. But log UCB actually allowed the set of arms to change also over time. The only thing was the features that described those arms, right, were assumed to be stationary. The feature set did not change, even though the arms themselves changed.
So for example, like every hour the news has to change. There is no option.
Yeah.
So the thing is that when compared to ads like Google ads or Yahoo ads, this would not be the scenario. Final word lim UCB for ads and then news for log UCB because of the less amount of time taken with log UCB? Or should we not take lim UCB for ads?
Should you not take lim UCB for ads? I wouldn't know. I mean, like I said, right, even the guys who worked on lim UCB are not using it for selection right now. And ad selection, in fact, it's not correct to say that ads do not change over time, because the advertisers are allowed to bid, okay, and they can bid at extremely low frequencies. I think they can change their bids every 5 minutes or something like that. So because they're changing their bids so often,
Bandit problem and go for a static copy rather. Yahoo want to do that.
I'm not sure. You had to ask that. Anyone from Yahoo here?
I saw a bag though, Yahoo bag.
Huh? I'm sorry?
I saw a Yahoo bag here.
So Yahoo bag. You know, they give those out for.
No, I used to work earlier in Yahoo.
Sorry?
I used to work earlier in Yahoo,
Yeah.
but I have not worked on. I worked on.
Not on the computational advertising. Not on the news.
So but still, why would they want to go for?
There could be multiple reasons. It could very well be that the kind of setting, you know, so there are too many imponderables that they were not able to take into account in the bandit setting. So I've actually sat through some presentations which had not completely got what they were trying to do there, but there's significant variation depending on time of day, and even the popularity of news stories vary very volatile fashion, and so on and so forth. So possibly that they found different ways of modeling that. It could also be that a lot of guys who are working on problems left Yahoo, which did happen. Almost all the names which I put in there as guys who work at Yahoo and who did all those work, none of them work for Yahoo anymore.
Startups?
No, they're at Microsoft, LinkedIn,
WhatsApp.
Amazon, not WhatsApp. Yeah. Not that I know of, but most of them are Moodle. I don't think that's the reason. I mean, they just the lab people couldn't sell it to the product team. So sometimes it's as mundane as the product team refusing to accept the innovation because they're not confident of it. Could very well be.
Thank you, sir.
Any question? So, let's give thanks to our respected speaker.